We're going to take a look at a pretty cool thing that we can do with our firewalls and routers across the network called quality of service, or what I'll refer to as QoS. So QoS is a pretty big topic, and I think you'll see very quickly that you can spend a lot of time and energy learning the intricate details of QoS, but we're going to take this from a step-by-step approach and kind of work through it just one piece at a time here. So the goal of this video is just to introduce you to the topic and then get our minds thinking a little bit about how we're going to use this in an enterprise or even maybe at your house or apartment type network. So why quality of service? Really what this is it's an idea that we can look at traffic on a network, whether it's by the source it's coming from, whether it's the type of application that we're dealing with, and then set it up as a priority in our network. So a good example of this might be, if you're in a business world, you might prioritize VoIP calls with clients over somebody watching Netflix, which we're hoping they're not doing at work in any case. But just kind of give you an idea of what style of thing we're looking at here. Where the need for this comes from is in the past, we used to be able to do what's called over-provisioning of a network, basically just putting more resources and more bandwidth in that network than it really needs. And the idea behind that was if we could put enough resources and bandwidth into a network, we could kind of accommodate for the peak usage times and everybody would still have a good experience. Well, now we're kind of hitting up somewhat of a limit here as we get more and more people connected, more devices, our applications are consuming more bandwidth. I like to use the Netflix example. If we're streaming in 1080p or 4K now, that's going to take more bandwidth, so this problem really isn't getting better as our technology develops as well. So it's something that you might want to start thinking about a little bit for how your business and whatever network you're on is going to be using it. So basically the way QoS works is the first thing we need to do is classify our traffic as it enters into our devices. We're going to look at it probably with a firewall here. And keep in mind, you can do this at the switching layer, you can do it at the routing layer, or firewalls, doesn't really matter, but layer 2 or 3 is what we're going to be working with. So as traffic comes into our network, we're going to classify it and figure out, is this high priority traffic? Is it low priority? Do we care if it drops packets? And start to figure out what we really need to focus on as our mission critical traffic and make sure that's getting to its destination, the most unimpeded and efficient routes that we can get there. So step one, we're going to classify that. We're not thinking about, I've been talking about stuff like, Netflix, but what we're really going to talk about in the end is not specific applications so much as we're going to talk about like video traffic or voice traffic or those broader categories of traffic as a whole. And so once we classify that traffic, we start to think about, how do we prioritize one piece of traffic over the next? So what's actually more important to me than the next? Is there a percentage I should be limiting that? Maybe giving one application 80% of my bandwidth? Does that application need 60% guaranteed? How do we figure that stuff out? Is this something that we're going to do during the peak usage hours, like an 8 to 5? And then after that, we just open up the bandwidth to everybody. So figuring those pieces out is really subjective. There's not a lot of, if your business is type X, you need to categorize your traffic as type Y. There's nothing really formal like that, so it's kind of up to each administrator a little bit like that. So I've posted one of the excerpts from the Juniper Day 1 implementing QoS books, and they have kind of this long definition of QoS, that quality of service. And one of the big takeaways that I wanted to have you guys recognize is that quality of service is something that needs to happen at each hop along that traffic's way. And this is something that we can only control inside of our networks. I can't control what my ISP uses for QoS. I can't control where that traffic goes after the ISP for QoS. But we need to make sure that we're conscious of how we're classifying and prioritizing this traffic across each device in our network. The big picture here is if I had maybe a couple of routers my traffic had to go through, then it hit the edge of the network. If one of those routers disregarded the QoS flags we can set and just treated all traffic the same, that experience is going to be diminished. So we got to be careful about this at each hop along the way. Class of service, or COS, some people just call it COS, is going to be just grouping that traffic together based on some sort of metric that we're going to use. We'll talk about that here a little bit as well. So what do you think of QoS? What do we think of? Why are we actually implementing this? Well, we see negative impacts on different types of traffic when we see a high load on a network. So maybe we've overcommitted some of our network resources, or maybe those links just don't support enough bandwidth, something like that. And there's three types of behaviors, they call it. You might call them detrimental effects or impacts to users that you're going to see where you need to start to think about QoS here. Number one is loss. So basically, we're just losing a packet. So I send a packet, it just doesn't reach my destination. And depending on the protocol, if we're using TCP, TCP will help us recover, but obviously we don't want to be losing packets across the network. Generally not a good thing. UDP, if we lose packets, we're sort of, just lost those packets forever. It's not a connection-oriented protocol, so there's some times where we use UDP traffic and quality of service might be a big impact to that. It's really easy to describe what loss is like for thinking about audio. So a lot of when you see QoS, people really focus on VoIP. So voice over IP is going to be something that's fairly bandwidth intensive, but the bigger picture is with VoIP, it's super easy to notice these behaviors that are going to make a call really terrible or really annoying to be a part of. When we lose packets in a voice over IP call, what you're going to hear is a simple click or a popping noise on the phone. Now, it's not something that would be maybe so detrimental that you can't have a conversation with, but think about if your speakers are consistently clicking or popping, that's going to get pretty annoying and pretty hard to work with over a series of time. So we call that still a loss-tolerant application because it doesn't completely destroy the functionality of it. If you want to think about something like loss-intolerant, this is maybe an oversimplified example, but something that helps us understand that point. If you're going to deposit money into your checking account or somebody's sending you a PayPal payment for $1,000, let's say, and the packet that contains that very last zero was dropped, and you only deposited or received $100, you're going to be pretty upset. And so we know that those types of applications cannot absolutely handle any loss at all. Fortunately, we have protocols like TCP where that's not really a big issue, but those would be like a loss-intolerant application. The next problem that we have is called latency. Latency is a pretty big one, and this is just the fact that when I send a couple of packets across the wire, some of those packets might take longer to reach the destination than the previous ones. And so the longer the time it takes for those packets to reach that destination, the higher latency we have. So think about this in the phone call scenario. If I was speaking to you and there was a big delay between a couple of my words, that would be pretty hard to have a conversation with. And that would be an example of latency. Those packets are getting there a little bit later on. Now, just kind of give you something interesting here since we're talking about this. The humans can really deal with about 200 milliseconds of latency without much noticeable trouble. So our brains can kind of correct for this latency, and even though it might not be the best quality conversation, we can still handle about those 200 milliseconds of latency. When you get to over 500 milliseconds of latency, we really start to have problems understanding and having that flow of the conversation be any good. So when we look at doing QoS for VoIP, there's going to be some metrics in there that we can plug in how much latency we can handle. That's going to help us figure out how we need to prioritize and shape that traffic. Now, a couple of real-world examples of latency as well. I put a picture up here. If I was streaming a hockey game, that hockey game is going to be broadcast. The computer that's broadcasting it has to process it. From the time that computer sends out that broadcast across the network until I get it, my screen is probably going to be a few seconds behind the broadcasting computer screen, just because there's network-introduced latency. Now, when we watch a stream like that, whether it's a hockey game or whatever you're watching online, that's called a unidirectional stream. They're presenting content to me. I'm not presenting any content back to them. It's a one-way street that way. Another way that you might see latency is when you watch the news. You'll see when they go from the main studio to a remote on-site reporter, they usually say we're going out to the field to a reporter, whatever their name might be, and the reporter stands there on screen for a few seconds not saying anything. So until they start broadcasting and they've gotten the okay, there's a little bit of latency in there, and that's when they start to notice that. The last behavior we're going to talk about is called jitter. Jitter is the idea that packets might arrive at a destination at different intervals. Now, this is somewhat similar to lag or latency, but it's just very slightly different here. So when jitter comes into play is when, again, if we talk about VoIP here, when I talk, it's an analog signal. My computer's taking that analog signal, converting it back to digital. So I have to be transmitting digital packets across the network. When the receiving end, maybe it's your phone, is getting that packet, it converts that digital signal back into analog packets, and then that audio is played to you. And that's how a simple VoIP conversation works. When we digitize these packets, the receiving end is expecting a steady stream of packets, maybe saying, I'm going to receive 100 packets every 10 milliseconds, or some measure that way. After those 10 milliseconds, I'm going to take all of my packets, decompress that data, and play audio. The problem with jitter is if I don't receive all of those packets within the specified interval, the decompressing of that data and outputting it to the user is going to fail. So we can increase the time that we wait for packets to arrive, but when we do that, we also increase our latency. That's called a de-jitter buffer, increasing the time we're waiting for packets. So now that you know some of the problems that we have on a network, we're going to look at a few of the solutions at a pretty high level today and talk about what we can do to go through this QoS process and make sure our users have a good experience here. So we'll talk about these at a high level. We'll move into a little bit more in-depth discussion, and then we'll start to implement these at each step of the way. So we've talked about classification a little bit. So we're going to classify traffic based on maybe a firewall rule or an incoming and ingress port and figure out, is this VoIP traffic, is it web, is it video traffic, and then apply this. Is it a high priority piece of traffic? Can we handle loss? Can it have jitter? What do we need to do with this traffic to make sure it's good? Once we figure out what the traffic is, we're going to place those in queues. Queues are like buffers for network traffic. A really easy way to visualize this is if you've ever boarded an airplane, we all get assigned a different boarding group. So think of these different boarding groups as our queues. The planes usually load in a specific order. Maybe it's just boarding group 1, 2, 3, and 4. So those might be our priorities, priority 1, 2, and 3, and 4. And based on what queue you're in or which line you're in on the airport is depending on when you're going to get on the plane. Same thing with our network traffic. Depends on when your packets are going to hit the actual switching fabric, the router or the firewall or the switch sending that packet out. There's a few other things we can do. We can do policing, which is where we basically set hard bandwidth limits. You can even set soft bandwidth limits, I guess, and tell specific applications or ports how much bandwidth they have. An example of this would be like when you subscribe to your ISP. You can buy a 20 meg plan from your ISP, you could buy a 50 meg plan or 100 meg plan, whatever they offer. They might be shaping your traffic with QoS by policing it. So if I pay for 20 megs of bandwidth, my ISP might put me in a QoS policy or policing policy saying any traffic coming in on this port gets 20 megs bandwidth. So that's kind of a common scenario you might see that in. We can also do what's called shaping, and that's basically where we say certain traffic can be sent up to this amount of bandwidth, and if we're reaching that limit, we're going to start shaping that, so scrunching it down, allowing for other traffic to pass through since this one is exceeding its traffic. Weighted random early discard is a really interesting concept, and it's a congestion avoidance scheme that takes advantage of how TCP works. We know TCP is a connection-oriented protocol, and every packet we send with the best effort is going to reach its destination. Even if it gets lost along the way, TCP will automatically have us retransmit that packet. So knowing that, what weighted random early discard is we will drop random TCP packets from our queues to shrink those queues down with the expectation that the application is going to pick that back up and retransmit the packets, so kind of buying ourselves a little bit of time. The last thing we can do is fragment and compress our traffic. To give you a general idea of this workflow here, we've kind of talked about this again, but it's nice to see it graphically. So we're going to figure out what kind of traffic we have, apply them to a class, so saying if they're high priority, low priority, what it might be. We're going to apply this to an inbound interface or an outbound interface, depending on how we want to set this up. Most commonly, we're going to do it on the ingress interface. And then based on our policing, or if we have the weighted random early detect, those types of things, that's going to help us shape this traffic and send that out the way. So let's look a little bit closer at classification and marking of traffic. Like I said, you can do this at layer 2 or layer 3. Now if you're in the Cisco world, doing the classification and marking at layer 2 is going to be a little bit faster. The reason being is we can use the ASIC hardware chips to do the classification for that. If you do it on layer 3, we're a little bit more dependent on the software running, and it's going to put a little bit more strain and overhead on our routers and firewalls. Not a huge deal at the end of the day, but just something you should be aware of. When we classify traffic, we can do it based on an access list, which would involve the IP address, a port, a protocol, no matter what we can put into those ACLs. We can do it based on an application type, so depending on if it's video traffic, voice traffic, we can classify that pretty easily. We could also do it on the trust state of a switch port. In layer 3, one of the common ways that we're going to mark packets is using what's called a ToS field, and I've got a screenshot of that coming up, and place in what's called a DSCP, or a differentiated service code point. These DSCP values identify how the traffic should be prioritized, maybe high priority, low loss, low priority, medium priority, whatever we want that traffic to be. There's some predefined DSCP values, so there's no need for us to reinvent the wheel. So in Juniper, we're going to see a lot of different terms, but these terms are pretty vendor neutral. So if you understand how we're going to do this in Juniper, you can understand it in different vendors like Cisco or Palo or whoever you might be using that for. So to classify traffic, and this is going to be our big overarching quality of service discussion here, we've got to look at a few different things, different steps to go through. So what I've got here on this screen is basically the steps that a packet's going to go through to get sent through a router or firewall supporting QoS. Let's start out with the forwarding class. The forwarding class is used entirely within a single network node, meaning it's unique to each router or firewall that the traffic passes through. The forwarding classes might be things like expedited forwarding, assured forwarding, best effort, network control. There's different classifications of traffic, and really all that means is, how much loss or latency can you handle? Is this high priority? Again, just a way for us to figure out where that traffic should go. You can see the 4 default Juniper ones, and we'll get into these here a little bit more once we go through that classification. But if you want to take a minute to read some of these descriptions of those forwarding classes, it gives you a little bit of an idea of what is happening in a forwarding class. The next thing we do is once we figured out what type of traffic that is and what forwarding class it should belong to, we're going to classify it. So there's a few ways that we can do this classification, and the 3 ways being interface-based, behavior aggregate, and multi-field classification. The most simple, rudimentary, and least flexible way to classify traffic is based on an interface. I can say any traffic coming into my firewall on port 1 is going to be high priority, low loss, low latency traffic. The problem with that is it's pretty inflexible. We're just going to treat all of the traffic blindly coming in on this port as whatever priority I suggest it is. We can get a little bit more complex and incorporate the interface-based classification with one of the other schemes like multi-field classifiers. And this is where some of that complexity of QoS starts to build. Typically when we see interface-based classification, we're going to see it on edge routers where we're just classifying all of our traffic from a remote router or a server. This could be your home connection to your ISP. They're going to get a certain forwarding class and a certain queue assigned to them. Behavior aggregate classification is where we trust our upstream partner, so the person sending traffic to us, to have marked their traffic correctly. So we're just going to look at the ToS field that they sent the traffic to us, what that contains, and based on that, we're going to trust them to classify it correctly, and we're just going to assign it to a priority queue and a forwarding class based off of that. Problem with it is you have to completely trust your upstream peers. If we go back to our example of if our traffic was being controlled by QoS to our ISP, if the ISP trusted us blindly, we could tell the ISP that we belong to a higher priority. We could classify our own traffic as being maybe that 100 meg plan. So that's not a very super common thing to see, but it is a way we can do it. So in addition, we have multi-field classification, which basically takes a firewall rule, looks at the traffic. If the traffic matches that firewall rule, we can put it into a queue or a class based off of that. This is really useful when we can't completely trust our upstream peers to mark their own packets. It takes some good firewall knowledge to get this up and running. After the multi-field classification, we take a look at policing. There's a few different ways we can do policing, and this is basically defining if traffic conforms to our rules, if it exceeds it, or if it violates it. Now there's some kind of goofy names that go with this. We have single rate 2-color, single rate 3-color, dual rate 3-color. When we see traffic color classification or policing, this is the way I think about it. This would be an example of 3-color. So your green is conforming, yellow is, hey, you're exceeding your traffic, and red might be you're violating the policy of how much bandwidth or what you're supposed to have. 2-color, you're basically either green, conforming, or red, violating. Let's take a look at these policing options here a little bit more closely. We're going to go with single rate 2-color. This means your traffic is either conforming to the bandwidth or the allotment that I've given you, or it's violating that as well. Think about this as if we had one big bucket. This bucket's going to get filled up with tokens, and those tokens get spent to allow traffic to go through. So basically when a packet arrives, our policer is going to check, do we have enough tokens in the bucket to allow that traffic to get through? If there's enough tokens in there, so if we have enough bytes available in our bucket, we're just going to simply allow the traffic through and take that number of tokens out of the bucket. There's a mathematical formula there that says over a period of time, and depending on how fast they're sending their traffic, we can start to refill the bucket with more tokens. It's a simple way that we can police the bandwidth being used by a router or a firewall. If you take a look at this, so if you had a packet, there was a delay of a second, another packet got sent, a delay of half a second, and a third packet got sent. If our policer was set to 128 bits per second, we could use that formula presented on the last slide to figure out, do we have enough tokens available in this bucket? So the formula was we would take basically 1 second, the time between packets, times our policer rate of 128 bits per second, and divide that by 8, and we get our 16 bytes. So that's that first 16 tokens you see. So between the first packet and the second packet, we take 16 tokens out of that bucket. So if we send a third packet left, so there's a half-second delay between the second and third packets. We take that half second times 128 bits per second divided by 8. That gives us 8 bytes. So the result of that formula is how many tokens do we put back into the bucket. So we're replenishing the bucket with that formula there. So depending on our packet sizes, kind of defines, are we spending more tokens than we really have is what we're going for with that. Now we're getting to the other policing options is we know that data across the network isn't necessarily smooth. So our packets aren't always the same size, they don't always arrive at the same rate. Some packets, like things that you see from VoIP, are what's called bursty. So they might send very little traffic at times, they might spin up and send a whole bunch of data if we're on an HD VoIP call, and other times that network is just quiet. So what we do here is we introduce a second bucket. We have our first bucket, the committed burst, and our second bucket would be the excess burst. We use the same replenishing formula that we used in the last set of slides here. Where we get to the single rate 3-color is, if we look at this bucket here, once the bucket's full, it can only hold so many tokens, but we're still going to keep trying to add tokens to them while there's quiet time on the network. Once we fill the bucket, those other tokens that we keep adding to it are just going to spill out. That person's limited to whatever bucket they were given. What we can do here with a 2-bucket or 3-color approach here is when that first bucket gets full, so we've replenished all of our tokens, we've got all of our bandwidth available to us, instead of just losing those tokens out into the middle of nowhere, we're going to start filling a second bucket. So when our traffic reaches an abnormal high, that second bucket can be used to fulfill our bandwidth requirements. Once the second bucket's full, same thing we have like we did before, those tokens just get wasted and thrown out into the middle of nowhere. The cool thing about this is, if a packet's small enough to be taken from our BC bucket, that committed bucket, it just gets sent through that. It's called conforming traffic or green traffic. If the traffic was a little bursty, there wasn't enough in the BC bucket, and we needed to dip into that BE bucket, we're exceeding, or yellow, but it's still allowed through. If our packets and we're sending so much data is so big, our BC bucket and our BE buckets combined don't have enough tokens, we're now violating the policy and we're in that red category. Dual rate 3-color, so before we still had single rate 3-color, now we're moving to dual rate 3-color. This is basically we have two rates that were given. Maybe it's by our ISP, maybe it's something that we've given to applications. They have a committed information rate, which they can normally use. They might have a little bit higher peak information rate. Maybe during certain times of the day, they can have a bigger bucket of tokens. Same idea here though. The BC bucket in this case, however, does not spill over into the BE bucket. They're two totally separate independent buckets. Next thing we had was that random early discard, and we talked about this previously, so I won't spend much time on it, but this was the idea that if we had traffic and there was congestion on the network, we could just drop random TCP packets from a queue, and those TCP applications will hopefully send out new packets. Problem with this is though, if we're doing this, we're going to treat all of our traffic as equal, and we're just going to drop it from random queues. The problem with that is in QoS, not all traffic is equal. Maybe we really do want VoIP traffic to be prioritized over things like video traffic. So by dropping packets from each of those, we're treating them fairly, but we're not necessarily following what we wanted to do with QoS. I also put a note here that we know UDP is connectionless, so we're not going to have that fail-safe. So if we start dropping UDP packets, they're just gone forever. Shaping is acting upon traffic that's already been granted to a queue. So depending on these queues, we're going to give them specific transmission resources. And anything that's in those queues that doesn't match the shaper's criteria just gets held in the queue until it conforms, and then it can be sent out across the network. This is one thing that's nice about it, is it can be less aggressive than policing, since we don't actually need to drop traffic or strictly hard limit traffic until our queues begin to get full. So only when there's congestion and there's problems are we going to start shaping. Next thing we have is scheduling, and that's deciding basically which order to put packets back on the wire based on what class they belong to. Really simple example of scheduling here. If we go back to talking about how we board an airplane, we know that we go onto the plane based on what queue we've been placed in. Q1 goes first, second is number 2, third is number 3. However, if somebody has a airline status, like a diamond or a platinum status, if you're a Delta flyer or whatever the United ones are, if you go up to your priority line, that red carpet line, you get to go out onto that plane before everybody else. That's an example of scheduling. Some queues may take priority over those other ones. The very last thing is remarking. So this is as we're sending traffic out, we've gone through all of this stuff on our device, we're sending it on to that next hop. Do we need to mark the traffic as priority, like high priority, low priority? That's where this behavior aggregate comes from. We're going to mark the traffic, send it out to that next downstream peer from us, and they're going to trust what we sent out. Now, interestingly enough, if you pull this up in Wireshark, do a packet capture, you can expand out your IP field on a TCP packet, and you can actually see your DSCP field there. So how is your traffic being classified on a network? And you can go look up these fields and figure out what they mean and get some kind of interesting information out of those. We've got some charts and things that we can look at too that'll help you understand DSCP. So this is the Juniper workflow for getting through quality of service, or if they call it QoS. A couple things that we need to just look at here. So we looked at this on the ingress. We're going to do our BA or our inbound interface or our multi-field classification. So that's kind of all included in that first block there. From there we go to policing and multi-field classifier. Those both use the same firewall construct. So for writing firewall rules for that multi-field classifier, that's going to be the same basically construct. How do we develop those rules for the policing? Next thing we do, we apply those to the forwarding classes and figure out, what loss priority they should have, what class do they belong to. We put it on the fabric. Fabric's just a fancy name for the actual part of the router or firewall that's sending the packets between interfaces. Next thing we do is we hit that egress policing. If we need to do any of the scheduling, shaping, or read, that happens before it gets sent out. Last thing we do is if we need to rewrite that priority field, that TOS field, we're going to send that out our egress interface. So I hope this kind of gives you a picture of at least the high-level workflow we're going to have to go through. Like I said, it is a very large topic. You can get really into the weeds on these different details. We're going to try to take it from some very practical approaches, get you started with it, and then let you run with those ideas afterwards. So that's all I've got for this video. We'll pick it up again in some practical configurations.